right, welcome back, students. This is the second lecture that I will be recording for our natural language processing class. It does not have to be the second lecture that you are listening to. You are free to engage with these lectures however interests you and however best serves the work that you're doing on your project. So today we are going to be talking about stemming and normalizing text, right? Which really just means how do we take text and break it up into smaller pieces. So for instance, how could I answer the question, how many words are in this sentence, right? So, and if I look at that sentence itself, how many words in a sentence? Okay, cool. I count 6, right? That shouldn't be that hard. Except as we've seen, spoken language, written language, human language don't like to follow rational or convenient structures, right? So for instance, how do we handle filler pauses, right? Or like fragments. So if I say I do mainly business data processing, right? Do we count as a word in that sentence? Do I count main and mainly as two different words in that sentence, even though one is just a fragment of the other? Right, so let's think about the sentence, Seuss's cat in the hat is different from other cats. Right, so if I ask you how many words are in that sentence, I could really be talking about two different things, right? One, how many lemmas appear in that sentence, where a lemma is just a group of words, a set of words that all share the same stem, the same root. So in this case, cat and cats would be the same lemma, right? Since they come from the same root. Or I might be asking you how many word forms, right? Where cat and cats would therefore be different, right? So the way a natural language focused data science would say that, right, is either how many types appear in the sentence or how many tokens appear in the sentence, right? So a token is a complete count of the word forms that appear in a sentence. A type is a count of the unique words that appear in a sentence, right? So if I look at this sentence fragment, they lay back on the San Francisco grass and looked at the stars in there. Well, the tokens there should be pretty easy to count, right? They lay back on 1, 2, 3, 4, okay, 15, right? 15 separate word forms there. Well, except what about San Francisco? Even though it's enunciated as two different word forms, San and Francisco, it's actually just one thing. Okay, so maybe it's actually 14, right? And if we count unique words, they lay back, right? We might find 13. But we might need to ask ourselves, hey, is like they and their, do those share a root, right? And with all of the these, do we want to consider an article as a standalone word? Or is the grass actually one word? Is that actually one noun? Is that one object? Right? So counting types and counting tokens, as with many natural language processing tasks, is much more nuanced than it first appears. Right? So a corpus is a collection of text, right? So today we're talking about corpora. Corpus just means body. Corpora is the plural of that, so it means several or many bodies, and it just means like a group of text, right? So if you scrape a bunch of emails, scrape a bunch of tweets, collect a bunch of novels, right? Just any collection of text we would call a corpus. And the number of words that appear in these corpora, right, since corpora is the plural of corpus, follows a slightly rational law, right? So what we would call Heap's law or Hurden's law, same thing, right? There is an observed relationship between the number of tokens and the number of types. Another way of saying number of types would be the size of the vocabulary that appears in a corpus, right? And this is an exponential relationship, right? So for n words, we expect to see kn to the power of beta unique words, right? So the size of vocabulary is given by kn to the power of beta, where k and beta are just some constants that are going to be sort of different for every corpus, which is kind of a bummer, right? Which is kind of a pain in the butt. It would be really cool if I could tell you, hey, that beta value, that k value, right? K is always 2 and beta is always 0.75. But it changes from body to body, right? Since words, the way language is used, changes based on a lot of different things, right? Each writer might have a particular vocabulary that they prefer, right? The time that a corpus was collected, right? Kind of the age of human development, right? So text from the 1800s and text from the 1900s and text from the 2000s. We expect very different vocabularies from those, right? Specific varieties, right? So business writing or academic writing or fiction, we expect all of these to have different vocabularies, right? Languages or specific intentions, right? There are many, many different things that affect the size and the nature of a corpus, right? And so to really understand how we should be approaching a corpus, there's a lot of little information that we need to understand about it, right? Including when and where and how it was collected, right? Because there are many different facets of language that can affect how it would appear, right? There's more than 7,000 different spoken languages in the world, right? And every one of them is going to have its own vocabulary and its own grammar, right? Even within language, we expect to see a large number of dialects, right? And it's true that speakers or people who are writing aren't bound to use the same language throughout the entirety of a corpus or even within a single sentence, right? It's common for people who speak more than one language to switch fluidly between those languages. So to work with a corpus, we need to understand a lot about it, right? We can't just scrape a bunch of material or download a billion emails and start going with it. So a well-curated corpus will come with a data sheet that's going to tell you some about why it was collected. What was the intent, not only of the writers in the corpus, what was the intent of the analyst who collected it, right? Who collected it? Who wrote it, right? Who funded it is an interesting question, right? Because that can influence the intent of the person who was collecting it, right? When was it written? Where was it written? Why was it written? When was it collected? Where was it collected? Why was it collected? Right? The data sheet. And this is sort of like, if you've ever looked at Kaggle, every data set will have like a data card on the front page of that data set, right? So getting the basic statistics, getting the basic concepts behind a corpus is an important first step to getting rolling with working with a corpus. Right, but let's start jumping into the nitty-gritty of like once we found this corpus and once we know when and where and how and why it was collected and when and where and how and why it was written, how do we start processing that? Right, so let's go back to our original question. How many words in a sentence? Right, tokenizing. Right, since tokens are individual word forms, tokenizing means breaking corpora or sentences into individual elements. Of course, once we have broken those sentences into elements, if we want to start recognizing how many unique words are in that sentence, we're going to have to go through the process of normalization. Normalization just means putting text into a more convenient or interpretable form. And that can include things like stemming, identifying words that share a common root. So for instance, cat and cats. So the simplest way that we could tokenize a sentence or a corpus, right, is just to look for the spaces. Right? And this is well supported in Unix. We're actually going to be using Python in this class, so don't worry too much about the Unix command line commands that are going to be given over the next few slides. Right? For this lecture, I'm using slides that are provided with our textbook, Speech and Language Processing, and you can get both of those in the links provided on Canvas for our class. Right, so dividing words based on space, right, is an easy first step, right? It's a simple process, but it gives us some troubles, right? Because again, like, language doesn't always behave the way we want it to. Because it wasn't developed rationally, it was developed organically, right? So if we were to take all of Shakespeare, right, and we were to separate all of it by spaces, and we were to reduce all of it to lowercase, right, and then count all of the occurrence of all of the tokens that we've collected, here we see that the author has identified nearly 9,000 instances of the word D, which is not currently a word, and I do not believe was a word in the time of Shakespeare, right? So it appears that something more complicated is going on here. It appears that we need to perhaps dig in a little bit more deeply. So, some issues that we need to consider when tokenizing, right? First of all, punctuation is going to sort of throw a wrench into our works, right? It would be very easy to think that a period always divides two sentences, but in fact that's not true, right? As punctuations frequently appear in sentences, or decimals frequently appear in sentences, right? Or URLs now frequently appear in sentences, or email addresses, right? Any one of those might have a period in a way that doesn't terminate a sentence, right? So we can't just naively remove punctuation, right? We might need an approach that preserves, for instance, prices or dates or URLs or abbreviations, right? We also need to think about what are called clitics, right? Which is just a word that doesn't appear on its own in a sentence, right? In English and in many Romance languages, this is most commonly contractions, right? So for instance, we're is the contraction of we are. Are is a part of that. It would be reasonable to say that are appears in the sentence, we're here now, except it's not written out, right? If we were just splitting on space, we wouldn't recognize that are appears in the sentence we're here now, right? And we might also need to consider, how do we deal with multi-word expressions? So San Francisco was an example of that several slides ago, or for instance, New York, right, should be a single word, or rather should be a single object that is expressed with several words, or rock and roll might be a single object that is expressed with several words. So how do we find those and recognize those? Right. In this class, we will primarily be working with English. Any of you that want to use a different language as your focus in your personal project, that is perfectly acceptable. But different languages, different rules, right? So for instance, some languages don't use spaces to separate words. So if we naively crafted a tokenizer that used spaces to tokenize corpora, and then we applied it to one of these languages, for instance, Chinese, which does not use spaces to separate words, we would get very poor results, right? So here we see an example of tokenizing a Chinese language sentence. Yao Ming reaches the finals. And we could potentially tokenize it this way, or this way, or this way, right? And so here it takes substantial domain knowledge, expertise, to just be able to split a sentence into base tokens, into the base objects contained in that sentence. All right, so let's talk about an algorithmic approach to tokenizing sentences, right? So one approach, which we've already seen performs poorly, would be whitespace segmentation. Or we could think of individual characters as tokens in a sentence, right? Which is convenient, which is easy to do, but it sacrifices all of the semantic significance of our tokens. So let's try to follow an algorithm. Let's try to conceptualize an algorithm which starts with the convenience of single character segmentation, right? Which starts with the discrete packets of characters and works towards a method of tokenizing based on words that doesn't rely on white space segmentation. So, for the next several slides, we will be talking about byte pair encoding. Right? Now, byte pair encoding is not the best method to tokenize sentences, right? But it is a good algorithm to get us started in our discussion, right? And essentially, we're going to propose a method which starts with character tokenization, which starts with breaking corpora into only the characters contained in that sentence, and then works towards building up word-level tokens, right, by learning the tokens that appear in a corpus. And let's see how we might do that, right? Well, as I've said, as I've kind of telegraphed here, we're going to start with all individual characters being recognized as tokens. And now we're going to repeat a learning process, right? We're going to observe a training corpus. We're going to observe symbols which appear most frequently, right? And notice this is symbols. This is not characters, right? We're going to start with characters as our symbols, but our idea is to build up more complex word-level tokens, right? So iteratively, we're going to choose the two symbols that appear most frequently adjacent to one another in our training corpus, right? So for instance, A and B, big A and big B, might appear most frequently together in our training corpus, and we're going to add a new merged symbol to our vocabulary, right? And then go through our training corpus and replace every occurrence of the two old symbols, A and B, which appear adjacently to one another, I should say, with our new symbol, AB. Right? So we started with symbols which were each individual characters, and now we've observed the occurrence of a new symbol, AB, right? And now we've adjusted our training material to reflect this new symbol, AB, right? And now we keep doing this, and we keep doing this, and we keep doing this, and we stop after some predefined K merges have been done. Right? And so the idea is that after several hundred, several thousand merges, we will have assembled through observation a vocabulary of the tokens that appear in our training corpus. Here is the formal pseudocode for doing that, but this is not an algorithm I expect you to be able to hand code. Right? This is more an interesting algorithm to understand in terms of how we could approach this problem of learning the extant tokens in a corpus, rather than approaching the problem with the predefined dictionary, rather than approaching a problem with the predefined set of words that we expect to find. One small addendum with byte pair encoding, right, is that we still want to avoid that space separation assumption, right? So it's a common pre-processing technique to go in and insert some end-of-word symbol, right? Which takes a bit of an assumption, right? You have to be able to recognize individual words before you can insert this underscore to represent the end of a word, right? So we should think that the training corpus, right, our training data for this particular algorithm is going to have a little bit of pre-processing that our real-world data wouldn't necessarily have, right? But that little bit of work is going to let us build our vocabulary for then later tokenizing some test material or real-world material. So as an example, let's think of a small corpus, right? This text in blue here, low, 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 lowest, lowest, newer, 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 wider, 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 new, new, right? Not a particularly interesting corpus, right? But if we were to use this as training data, we would need to go in and insert an end of words token. And then by separating each word into its base characters, we would have built up a vocabulary shown here at the bottom of the screen. All right, now let's think what would happen over some number of iterations. Right? We've got 5 occurrences of low and 2 occurrences of lowest and 6 occurrences of newer and 3 occurrences of wider and 2 occurrences of new, right? So by observing, we see that little e and little r are the 2 characters most likely to appear adjacent to one another. So we add that new symbol to our vocabulary, and then we adjust our training material, right? So in the bottom half of our screen, we see that our vocabulary has been updated, and we see that our training data has had every adjacent occurrence of E and R replaced with the new symbol ER. Okay, and then we observe again and replace again. And then we observe again and we replace again. And observe again and replace again, observe again and replace again, right, until we've performed this merger k times, where k is just some predetermined constant, right? And we end up with the vocabulary shown on the bottom line of this row, which is all of our base characters. Notice we have not removed our base characters nor our end of word token, right? But we've learned that newer and low are words in our vocabulary, right? So we have learned to represent tokens. Now, we haven't learned the entire language yet. We still have some training to do, right? So our arbitrary k would need to be a little bit larger for this to work, right? We can also see here that these joint like combined symbols, for instance, new, NEW, and ER, can also be merged together to give us the newer symbol, right? So we won't always be putting together base characters. We won't always be adding just one character to a new symbol, right? We can merge symbols, and by doing that, we learn a vocabulary. Good. Once we've learned our vocabulary, we're now ready to go out and look at some test data. And to tokenize our test data, we would greedily search for the learned tokens, right? And what do I mean by greedy? I just mean find the biggest token first, right? So new and newer are all in our vocabulary. Looking at our test data, we would want to find newer before we went in and found any occurrences of new, right? So greedily just means eat up as many characters as possible each time we select a token from our test data. So an interesting thing about base pair encoding, is that it's going to present for us our most frequent words as tokens first, right? Which can be useful in building a vocabulary. And it's also going to give us the set of frequent morphemes in our language, where a morpheme is just the smallest meaning-bearing chunk in a language, right? So for instance, in the word unlikeliest, we could find 3 morphemes. Un, right? We all recognize that un has a meaning, right? Likely has a meaning, and ist has a meaning, right? Un is like a logical negation in a language. Likely means probable, and ist means it's the most of something, right? So all 3 of those morphemes would have been found through the process of base pair encoding, right? So base pair encoding doesn't just give us word level tokens, it also gives us sub-word packages of significance in our language. Okay, so we can break up a corpus into words now, right? We've got a few tools to do that, right? We've got white space separation. We've got, regular expressions could let us find words separated by more complex, right, separators than just white space. We've got base pair encodings. And we've still got some stuff to figure out, right? Because even if we've gone through our entire corpus and we've separated out every individual word, we're still not ready to answer the question, how many words are in a sentence, right? Since, let's consider USA, right? The name of our country. Should we consider U.S.A to be a separate word from USA? Well, no, clearly not. They're both the same thing, so we need to figure out a standardized form for those two words, right? Or right? Sort of the non-word noises that might be recorded in a language. Do we have a standardized form that we can write that out, right? Words that appear at the beginning of a sentence are going to be capitalized, but they're the same word as the uncapitalized version that appears in the middle of a sentence. So, for instance, fed or fed. And am, is, be, and are all conjugations of the same word, right? They all share a similar stem. So, tokenization is still not our answer to how many words are in a sentence, right? Now we need to talk a little about normalization. And the techniques of normalization that we choose to apply are going to be dependent on the task that we are trying to solve, that we're trying to address, right? So to answer the question, how many words appear in a sentence, or what's the size of our vocabulary, case folding, right, which means reducing all of our words to, for instance, lowercase or making them all uppercase, is a great thing to do, right? Since that way fed and fed appear as the same word when we want them to be the same word. That's perfect, right? But if I was answering a different question, for instance, how does this writer feel about the subject? Well, case might be very, very helpful, right? Especially with like material scraped from the internet. If something is written in all caps, that should be an important consideration if I'm doing something like sentiment analysis, if I'm trying to figure out how the speaker feels about the subject. So our intent is going to define the process of normalization. So normalization is not a homogeneous process. Normalization means putting words into the form that is most convenient for the task that we're trying to solve. Lemmatization means looking at a word and identifying its base, right? We've said earlier that lemmas are all words that sort of live in a set, right? So one lemma is sort of this set of words that all share the same stem. So for instance, am and are and is all share the stem be, right? Car, cars, cars possessive, cars plural possessive, all share the base car, right? In Spanish, quiero, quieres are conjugations of the base verb querer, right? To want, right? So, conjugation, where we alter a verb depending on who that verb is applied to, or altering a noun to show plurality or possession, right? Undoing that would be a process of lemmatization, right? We might also need to consider tense in lemmatization, right? Verbs that happened in the past are still the same words as verb that happen in the present, right? Or he is reading detective stories, which is happening currently, or he be read detective story, right? These are, in this case, is and be should be recognized as the same word, right? Just expressed differently in two different sentences. All right, so a fundamental process of lemmatization is removing morphemes that kind of get stuck onto a root word, right? So for instance, un was a morpheme that we saw earlier, right? By removing that morpheme, we could find the stem, the root word, right? So in unlikeliest, we see a stem likely with two affixes, right? Where an affix can be a suffix or a prefix, right? It can come before the stem or after the stem, and it's just a little morpheme, a little meaning-bearing unit that gets smushed onto a base word, right? So a morpheme might also be the S or ES used to pluralize a noun. So by stripping these off, we're doing what's called stemming, right? Removing affixes to find the stem of a word. And in that way, we would be able to count the vocabulary of a sentence, right? Count the types that appear in a corpus, not just the tokens. And when we're doing that, right, we do need to consider morphemes are meaning-bearing units of language, right? If we remove them, we're altering the meaning of a word, right? So this stemming is kind of a destructive process. If we're going to stem, we're going to change the meaning of a sentence, right? So if we start with this sentence on the left, this was not the map we found in Billy Bones' chest, so on and so forth, right? And apply some process of stemming, we end up with a sentence that is maybe interpretable, right? If you really squint and try, you could figure out the one, not the map we found. You could see what that means, right? But by performing one task, counting a vocabulary, we've had to sacrifice some of the meaning in this sentence, right? So anytime we apply normalization, we need to be aware of the task that we're trying to perform, right? So stemming is useful for some tasks and not for all. So how could we go about performing stemming, right? A base algorithm for performing stemming is called Porter stemming, right? Or rather, the Porter stemmer. The text that you saw in the previous screen was processed using the Porter stemmer. And the Porter stemmer works by applying a hierarchical series of words, right? So maybe not hierarchical, an ordered series of rules, right? Which alter words to reveal their stems, to reveal their bases, right? So some samples of these rules, for instance, anytime we see ational in a rule, we will replace it with ate. So for instance, relational will be replaced with relate. Ing can simply be removed generally, right? So motoring is replaced with motor. SSES can be replaced with SS, right? So grasses is reduced to grass. Right, and so this is applied iteratively in several passes, and these rules are not learned, rather they have to be defined by a linguist, right? They're language specific, and they're really period and intent specific too, right? So the Porter stemmer is one technique which allows us to iteratively apply these rules to find stems of words in a corpus. But again, right, stemming is extremely language dependent, so the Porter stemmer is sort of defined for the English language, but every language needs to have its own rule set. And finally, one last thought on tokenization. Right, earlier we were looking at techniques for dividing a corpus, some chunk of text into words or even morphemes, right? But we will also frequently need to divide a corpus into sentences, right? And so just like white space division was our sort of naive approach to dividing words in a text document, period division would be the easiest way to separate text into sentences. But again, we're going to have issues there, right? So sentence segmentation Sentence segmentation is a piece of vocabulary that the authors of this textbook have chosen to run with. Oftentimes, this is just called sentence tokenization, right? Since token is really kind of nebulously defined, right? In the context of our textbook, we're using token to mean a single word, but there's no reason that a sentence couldn't itself be a token, right? Since a sentence sort of has a meaning, right? So, just to avoid confusion, our authors refer to tokenization exclusively as splitting text into words, and use segmentation to refer to the process of dividing text into sentences. And again, we can't just assume that a period is the end of a sentence, right? Since again, they appear in abbreviations, they appear in decimals. It's not specifically mentioned on this slide, but it is acceptable in English to use an exclamation point in the middle of a sentence, right? So how do we divide based on punctuation? It turns out it's not that much easier. And it can be easier to tokenize down to words and then rebuild sentences based on that. All right, that is all the slides that we have for this portion of the textbook. So please rejoin me in just a second while I pull up my IDE, and we will look at some tokenization and normalization in practice using the Python language. All right, welcome back to the coding portion of this lecture. Right, so we've sort of looked at the basic ideas behind some of the techniques for tokenizing and stemming and normalization. Now we're going to see how those look in practice using the Python language specifically, right? So we saw in the slides that our authors preferred the Unix built-in text processing tools. Python is kind of our language of instruction for this class. So we're going to be reperforming some of the same tasks in Python. And today I've got for us some text. This is just the Wikipedia article, The Early Life of Noam Chomsky. Noam Chomsky was an extremely influential linguist. You've probably in class already heard me give his example sentence about the colorless green idea sleeping furiously. Right, so a lot of the ideas we're discussing in this class go back to Noam Chomsky, so I thought it would be fun to kind of get some of the text about his early life growing up in Philadelphia. And let's answer that question of how many words appear in this text, right? How many words? That's the question we've been trying to answer all day. So I've gone ahead and downloaded us some tools that we might need today, right? NLTK is the Natural Language Toolkit. It's something we're going to be using a lot in this class. And y'all should already know, I don't code without my documentation, right? I normally have a dozen different tabs open when I'm writing code. So I've gone ahead and got myself the documentation for some tokenizers from NLTK and the Porter stemmer from NLTK, since they have a version of the Porter stemmer with the stemming rules already written into it provided, right? So we're going to be using NLTK today, and let's see what that's going to look like, right? So I've got a variable named text. We don't have to worry about reading a file. I thought we would do this the easy way this time. And let's just ask ourselves first, how many sentences appear here? Right? And I see 1, 2, 3. Well, it's going to take a while if I try to do this by hand. So let's use the tools that NLTK provides for us. Sentences. I can get this using the tokenize module in NLTK. And specifically, I want to use the sent tokenizer, right? And this is kind of what I was saying earlier with our authors for our textbook use sentence segmentation to refer to splitting text into sentences. NLTK prefers to call it tokenizing with a sentence as the base token. Same thing. And all we need to do is pass text to our tokenizer. And then let's see how many sentences we get back. Length of sentences. 18. Let's see. Does that sound right? Well, we can check this. I guess an easy way would be print sentences of 0. And then let's print the last one and make sure that every sentence in our text, what am I doing? Sentences of -1 is just the last in a list. 18 sentences. The first of them, Chomsky was born December 7. Chomsky was born December 7. Good. And now Chomsky was firmly. And here we go. Last sentence, Chomsky was firmly. Yes, so I wasn't sure if that 18 number was correct, but it does look like it has correctly divided this text into sentences. And we can see here that it's preserving the new lines that I added just to keep this text under the 80 characters here. Okay, cool. So that's our sentence segmentation. Let's try word segmentation now. Words is equal to NLTK dot tokenize text. All right. And let's print. Oh, how many words are there? Lynn, words. Let's see. Uh-oh. NLTK tokenize. Oh, here we go. Dot word tokenize. Okay, 453 different words. And let's see what it thinks those words are. Let's just print that raw list. Chomsky. Okay, good. That's our first sentence. Was. Okay. Born. Good. On December 7, comma. Uh-oh. Because it thinks that comma is a token. 1928. Oh, and here's another comma included in the list. Okay. So, Philadelphia, Pennsylvania, and yeah, look, the period at the end of the sentence has been. So it's really good at splitting up words, but it looks like a lot of punctuation has been included. Okay, so 2 different ways that we can address this. One is regular expressions, right? So if you have watched the video on regular expressions, this will be pretty natural to you. Otherwise, hey, regular expressions are something you should circle back and learn at some point, right? They're a great tool. And this is one of the reasons why. Let's use perhaps the regex tokenizer instead of... So here, yeah, it looks like with our regex tokenizer, we can provide not just the text that we want to divide, but also a pattern that we're going to use to divide that text. Awesome. So let's grab some of this and copy it over and see if we can get this to work. And here we go. I've copied some stuff over, and I paused the video for a second just to alter this so it'll fit our purposes. So the regular expression I provided it is, hey, a token should look like this. So that R in the front means this is a raw string. And now I'm saying, hey, /W is any alphanumeric character. Plus means one or more occurrence of that. And now let's just print what it will think that our words are. Give this a play. Oh, and of course I didn't want to print the tokenizer. I wanted to print the word list it returns. So let's There we go. Let's actually catch the return of this function so that we can do that. There we go. And let's see what we get back. Chomsky was born on December 7, 1928. And okay, this is looking good. So I'm not seeing any punctuation showing up here as an element in our list. Okay, cool. So it looks like we've done a good job of now only capturing tokens composed of one or more white spaces. The problem here is that we're going to divide tokens that contain non-alphanumeric characters. So for instance, hyphenated words are not going to appear as a single token in our tokenizer here. Okay, cool. So two approaches to that. One is that we could adjust our regular expression here, right? So I could say like maybe an optional hyphen and then 0 or more occurrences of an alphanumeric character, right? So now hyphenated characters will appear in there too, or hyphenated words will appear in there too, right? Another approach that I want us to try is to go back to what we had originally, and let's just go through and remove everything that is punctuation, right? Since the word tokenizer provided by NLTK works quite well, it's just giving us some extra junk that we need to take out. So let's see how we can do that. Word for word and words. I'm using a list comprehension to do this. List comprehensions in Python are extremely powerful and useful. So if this isn't a tool that you've used a lot in the past, I suggest you get familiar with list comprehensions. So we need to put a condition on this, right? If word is not a piece of punctuation, right? So I just need to figure out how to do this. And fortunately, this string library gives us a list of all possible punctuation. So check this out. String dot punctuation. If I run this, look at that. It gives me this string, right? I can tell that this is a string because it's encapsulated here in single quotes. And I can use the in keyword in Python to check for inclusion as a substring in a string, right? So let's see if I can do that. So let's see, if word not in string dot punctuation, and then if we print words, Chomsky was born in, hey, look at this. Awesome. Okay. So, two techniques, one of which we sort of hand-jammed our own regular expression to define what we think a token is going to look like. One, we used the built-in NLTK word tokenizer and then took out some of the punctuation that it erroneously included as tokens, right? So, two approaches, kind of both equally alike in dignity. It's really down to which approach seems the most intuitive to you. Is writing a little list comprehension like this easier than writing a little regular expression like this? And really, at the end of the day, you should know how to do both. Okay, cool. So now, len words. Now we see that there are 404 words in our list, but we're still really not answering the question of how many unique words, right? So notice here, in and the and on and was, right? These are words that are probably going to appear many times in this text, right? So let's start doing the work of counting unique words, right? Let's get a word count going down here. And I'm going to do this as a dictionary, right? Any of y'all who have taken a class with me in the past, and all of you should have taken a class with me in the past because I'm the only one that teaches Intro to AI, at least in spring 2025, that's true. So, any of y'all who have taken a class with me know I kind of love dictionaries. They're extremely powerful and useful in Python. So let's use a dictionary to count how many times each word shows up. And maybe that'll give us a better understanding. Okay, so for word in words, word count of word is equal to word count dot get word comma 0, and I will add 1 to that. Okay, cool. So this just says, hey, look in the dictionary. If you find the word, return the value, right? If you find word as a key, return its value. Otherwise, return a default value of 0. We'll add 1. Ooh, what is that? There we go. We'll add 1 to it. Cool. And now let's print len word count. Oh, cool. So now 243 unique words. Huh. So that's way less than the 404 that we had a second ago. So now we're getting a better understanding of our vocabulary, but I'm just printing the raw word count itself. So the word Chomsky shows up 7 times. That kind of makes sense. Was born. Okay. Neighborhood of. Yeah. Oh, here's an interesting one. His, capital H-I-S, appears once. But I'll bet if we look, lowercase h-i-s is in here too. Huh. So we probably don't have a complete understanding of our vocabulary just yet. So let's go through. Let's just put everything in lowercase, right? To compensate for that. And I can actually do that up here in my little list comprehension where we remove the punctuation. This is just sort of the laziest way to do it. I can use .lower, which is a string method in Python. And now let's run this again. And now if I print, okay, cool. So now we see all of our keys are in lowercase. And if I scroll, maybe we'll see his again. Here now we have lowercase his shows up 9 times. So I bet a second ago we had 1 uppercase his and 8 lowercase his's, and now we're counting them all the same. So now we're down to 236 unique words. So we've got a few less, but we're not done yet. Right? We're not done yet. Because we're not really counting unique words yet. Right? So here, worked shows up as a token in our corpus, right? But worked isn't really a unique word, right? It's really just work and a suffix. So let's see if we can stem our tokens to find how many truly unique types. What is the actual size of our vocabulary in this particular sentence or in this particular corpus? And to do that, I'm going to try using the NLTK Porter stemmer. Oh, look at this. And the Porter stemmer itself is smart enough to convert things to lowercase, so that is handy. All right, and I'm just going to copy and paste over some code into our code book to get us started. There we go, and as promised, I have copied over the instantiator for our Porter stemmer class. It's just called stemmer. All right, so now stemmer is going to take one word at a time and provide its stem, its base, right, by iteratively applying those rules that we were discussing earlier, right? So let's just see what this looks like. I'm going to pass it the word running. And what we expect to see is run or something close to that. And of course, to call an instantiator, that is a method. So there we go. So that's how I've managed to get this error here. Okay, cool. Look, so the stemmer, by applying its rules, was able to find the root run from the word running. Or if I give it runs, we should expect to see the same thing. This is a little bit more tricky. I don't know if it's going to be able to get, it can't get run out of ran. But it'll at least give us a little bit more of insight into how many actual unique words appear in our corpus, in our little text about Noam Chomsky up here. Okay, cool. So we just need to feed one word at a time into our stemmer. We can do that with another little list comprehension. So I'm just going to replace my words list with a new list of words. Stemmer.stem word for word in words. Okay. And now we're down even farther. We've got 227 unique words. If we take a peek into exactly what we've got, Chomsky was born on December 7, 1928 in the East. Okay, cool. So notice here we've lost a little bit of our meaning, right? So the word was, the stemmer thought that that was plural and shortened that to the singular wa, right? So we've lost a little bit of our meaning, but we've applied the normalization that was appropriate for our task, right? Which in this case included Porter stemming and has given us, I think, the best possible estimation of our total vocabulary. 227 is what we are currently at. Of course, we could go through and maybe remove like numerals from our vocabulary, things like that. But the code we have seen so far has done a pretty good job of demonstrating three important processes: sentence segmentation, words tokenizing, and stemming or lemmatization. So, with that, I'm going to conclude this demonstration, and I will see you in class and in future lectures.